Hello, welcome to the last part of the talks about current and potential dividers. This time introducing Millman's theorem. And Millman's theorem is an extension of the potential divider equation. It addresses the problem: not all potential dividers have one end connected to ground. Some of them look like this. Right. How do we solve that? Well, we could go back to first principles. And first principles would indicate that we do something like this. We'd take our 160 millivolts that we know is the voltage of this node in the circuit here. That's going through a resistor of 330 K to a point where we're told the voltage is 100.6 millivolts. And then we go through another resistor, which we're not told the value of, to a point where we're told the voltage is 16 millivolts. So we could apply Ohm's law to this 330K resistor there. We know the voltage across it. That's just 160 millivolts, or 0.16, minus 0.1006, 100.6 millivolts. We know the value of the resistance, 330K, so we can work out the current flowing through this resistor here. That's just 1.8 times 10 to the power of minus 7, which is 180 nanoamps. The current flowing through this resistor must be the same as the current flowing through that resistor by Kirchhoff's current law, because no current can flow down through the voltmeter. It has an infinite resistance. So we know the current flowing through this resistor. We know the voltage across this resistor. We must be able to work out that resistance. Resistance is the change in voltage, delta V, over the current. In this case, that's 100.6 millivolts minus 16 millivolts divided by 180 nanoamps. And we can just work that out and get 6 minus 16 milliamps, 16 millivolts rather, divided by 180 nano is 4.7 times 10 to the power of 5, which is 470K. So our unknown resistance must be a 470K resistor. Well, yes, once again, fine, but it would be nice to have a formula that we could directly apply to problems like this, rather than have to go back to first principles every time. And that's exactly what Millman's theorem is. Consider this more general case. You have a voltage source here, which I've called a voltage of A, going through a resistance of R. A voltage source here, B, through a resistance of S, a voltage source C, through a resistance of T. I could carry on and put as many voltage sources through resistors as I wanted, join up these ends of all of the resistors, and Millman's theorem tells me what the voltage is at this junction. This is the formula that you get. Now, how you derive that? There's several ways to derive it, but possibly the simplest way to think about it is Kirchhoff's current law. Consider this node here, the common joint where all of the resistors meet up. Kirchhoff's current law says that the total current flowing into this node must be equal to the total current flowing out of this node. Or the total net current flowing into the node must be 0. Let's use that second form of Kirchhoff's current law. In general, let's consider the situation that we have a voltage, I'll call it V01 here, through a resistor R1, and V2 through a resistor R2, and V3 through a resistor R3, and so on. And they all meet up. And the voltage at this point here is Vout. Okay, let's apply Kirchhoff's current law to this node. The current flowing through R1 is going to be, applying Ohm's law to R1, V1 minus Vout divided by R1. That's the voltage across the resistor, V1 on this side, Vout on this side, divided by the value of the resistor. So that is the current flowing through here. I'll call it I1. The current flowing through this resistor, I'll call it I2. And the current flowing through this resistor, I will call it I3, and so on. So I1 is V1 minus Vout over R1. Apply Ohm's law to R2, and we get I2 equals V2 minus Vout over R2. I3 equals V3 minus Vout over R3, and we could carry on like that. And Kirchhoff's current law tells us that the total sum of all of these currents must be zero, because there's no current flowing out of this node. No current flows through the voltmeter, it has an infinite resistance. So, the sum of all of these currents must be zero. Therefore, V1 minus Vout over R1 plus V2 minus Vout over R2 plus V3 minus Vout over R3 plus, and so on, if I had more of these, must equal 0. Move all of the Vouts onto one side of this equation, and I would be left with V1 over R1 plus V2 over R2 plus V3 over R3, and so on, equals Vout over R1 plus Vout over R2 plus Vout over R3, and so on. Collect the terms here, and I would just get Vout times 1 over R1 plus 1 over R2. You may be able to see where this is going now, is the sum of all of these. Now I can write these using summation notation. The sum of Vi over Ri summing all over indices I. And that just means this sum here. I take V1 over R1, I add it to V2 over R2, add it to V3 over R3, and so on. And that is Vout times the sum of 1 over Ri summed over I. That just means 1 over R1 plus 1 over R2 plus 1 over R3, and so on. And that allows me to write the output, Vout, in the fairly simple form. It's the sum over I of Vi over Ri divided by the sum over I of 1 over Ri. And that is the final form of Millman's theorem, which gives you the output voltage here at the junction where you have a large number of resistors and voltage sources all joining up at one point. It's a useful thing to know, especially for some of the more advanced topics in the quiz app. Okay, that is the last topic and the end of this series of chats about current and potential dividers. You should now be ready to have a go at the topic in the quiz app. Good luck.